Section 1. Forces within Earth. Stress and strain. Along the boundaries between two tectonic plates, rock in the crust often resists movement. Over time, stress builds up. Stress is the total force acting on crustal rocks per unit of area. There are three kinds of stress that act on Earth's rocks: compression, tension, and shear. Compression causes a material to shorten. Tension causes a material to lengthen. Shear causes distortion of a material. The deformation of materials in response to stress is called strain. You can see the different forms below. Even though rocks can be twisted, squeezed, and stretched, they fracture when the stress and strain reach a critical point. At these breaks, rocks can move, releasing the energy built up as a result of the stress. Earthquakes are the result of this movement and release of energy. Elastic deformation is caused under conditions of low stress when a material is compressed, bent, or stretched. When the stress is removed, the original material returns to its original shape. When the stress builds up past a certain point, called the elastic limit, the rocks undergo plastic deformation. This type of strain produces permanent deformation. Most materials exhibit both elastic and plastic behavior. As the pressure increases, rocks require greater stress to reach the elastic limit. At high enough temperatures, solid rock can also deform, causing it to flow like a fluid-like manner. This flow reduces the stretch. Crustal rocks fail when the stresses exceed the strength of the rocks. The resulting movement occurs along a weak region in crustal rock called a fault, which is any fracture or system of fractures along which Earth moves. Reverse and normal faults. Reverse faults are on the right. They form as a result of horizontal and vertical compression that squeezes the rock and creates a shortening of the crust. This causes the rock on one side of the reverse fault to be pushed up relative to the other, whereas movement along a normal fault is partly horizontal and partly vertical. The horizontal movement pulls the rocks apart and stretches the crust. Vertical movement occurs as the stretching causes the rock on one side to fall down relative to the other side. So a compression reverse fault allows one to be pushed up, where an extension or a normal fault allows one to slide down. Strike-slip faults are caused by horizontal shear. The movement at these faults is mainly horizontal and in opposite directions, similar to the way cars move in opposite directions on a freeway. Irregular surfaces in rocks can snag and lock along faults when movement occurs. As stress continues to build in these rocks, they undergo elastic deformation. Beyond the elastic limit, they bend or stretch. Before that limit, an earthquake occurs when they slip or crumble. The vibrations of the ground produced during the earthquake are called seismic waves. Every earthquake generates three types of seismic waves: primary waves, which we call P waves, secondary waves, which we call S waves, and surface waves. The primary waves, also referred to as P waves, squeeze and push rocks in the direction along which the waves are traveling. Now notice it is just moving horizontally. Secondary waves, called S waves, are named with respect to their arrival times. They are slower than P waves, so they are the second set of waves to be felt. S waves have a motion that causes rocks to move perpendicular to the direction of the wave. The third and slowest type of waves are surface waves, which travel only along the Earth's surface. Surface waves can cause the ground to move sideways and up and down like ocean waves. The focus of an earthquake is the point of the initial fault rupture, which is usually several kilometers below the Earth's surface. The point on the surface directly above is called the epicenter. Section 2. Most of the vibrations caused by seismic waves cannot be felt at great distances from an earthquake's epicenter, but they can be detected by sensitive instruments called seismometers, which measure the horizontal or vertical motion during an earthquake. The frame of a seismometer is anchored to the ground. When an earthquake occurs, the frame moves, but the hanging mass and attached pen do not. The mass and the pen record the relative movement as the recording devices move under them. The record produced by a seismometer that can provide individual tracking of each type of wave is called a seismogram. And on the seismogram, you can see the three different areas where the waves are. The first set are the P waves, the second set are the S waves, and the large set at the end are the surface waves. A travel time curve provides the average time it takes for a P and S wave to reach seismic stations located at different distances from an earthquake's epicenter. Waves recorded on seismograms from more distant stations are further apart than waves recorded on seismograms at stations closer to the epicenter. The separation of seismic waves on seismograms can be used to determine the distance from the epicenter of an earthquake to the seismic station that recorded the seismogram. Seismic waves change speed and direction when they are at boundaries between different materials. As P waves and S waves initially travel through the mantle, they follow a fairly direct path. When P waves strike the core, they're refracted, which means they bend. To find out what happens to S waves generated by an earthquake, seismologists first determined that back and forth motion of S waves does not travel through liquid. They then noticed that S waves do not travel through the Earth's center. The data collected for paths and travel times of the waves inside Earth led to the current understanding that Earth has an outer core that is liquid and an inner core that is solid. Seismic waves change their speed as they encounter boundaries between the different materials. The travel times and behavior of the waves provided a detailed picture of the Earth's internal structure. These waves also show clues about the composition of the various parts of Earth.
Visualizing seismic waves. You may have felt seismic waves, but did you know that seismic waves travel through Earth? The travel times and behavior of seismic waves provide a detailed picture of Earth's internal structure. These waves also provide clues about the composition of the various parts of Earth. An earthquake sends seismic waves through Earth. P waves, or primary waves, in the outer core are refracted. This generates a P wave shadow zone on Earth's surface, where no direct P waves appear on seismograms. Other P waves are reflected and refracted by the inner core. These can be detected by seismometers on the other side of the shadow zone. S waves, or secondary waves, cannot travel through the liquid outer core and thus do not reappear beyond the S wave shadow zone.
Because the speed of seismic wave depends on the temperature and composition, it is possible to use seismic waves to create images of structures such as slabs and plumes. In general, the speed of seismic waves decreases as the temperature increases. Images like this one from Japan are generated by capturing the path of seismic waves through the Earth's interior. Measuring and locating earthquakes. The Richter scale, devised by a geologist named Charles Richter, is a numeric rating system that measures the magnitude of an earthquake. Magnitude is the measure of the energy released during an earthquake. The numbers on the Richter scale are determined by the height, called the amplitude of the largest seismic wave. The moment magnitude scale is a rating scale of the energy released by an earthquake, taking into account the size of the fault rupture, the amount of movement along the fault, and the rock's stiffness. The modified Mercalli scale is used to measure earthquake intensity on a scale from 1 to 12. The higher the number, the greater the damage the earthquake has caused. The intensity of an earthquake depends primarily on the amplitude of the surface waves generated. Maximum intensity values are observed in the region near the epicenter. Mercalli values decrease to 1 at distances far from the epicenter. Earthquakes are classified as shallow, intermediate, or deep, depending on the location of the focus. Shallow focus earthquakes are the most damaging. The location of an Earth's epicenter and the time of the earthquake's occurrence are usually not known at first. However, the epicenter's location as well as the time of the occurrence can be determined using seismograms and a travel time curve. Seismologists determine the distance to an earthquake's epicenter by measuring the separation on any seismogram and identifying that same separation time on the travel time graph. To locate the epicenter of an earthquake, scientists identify the seismic stations on a map and draw a circle with the radius of the distance to the epicenter from each station. The point where the circles intersect is called the epicenter. Seismologists can use a seismogram to gain information about the exact time that an earthquake occurs at the focus. The time can then be determined using a table similar to a travel time graph. The majority of the world's earthquakes occur along narrow seismic belts that separate large regions with little or no seismic activity. The locations of most earthquakes corresponds closely to that of the tectonic plate boundaries. Earthquake hazards are factors that determine the severity of damage produced by an earthquake. Identifying earthquake hazards in an area can sometimes help to prevent some of the damage and loss of life. One type of damage caused by earthquakes is called pancaking. Shaking causes a building supporting walls to collapse and the upper floors then fall on one another like a stack of pancakes. If the shaking caused by an earthquake has the same frequency and vibration as the natural sway of buildings of certain heights, those buildings will sway the most during an earthquake. Shorter and taller buildings, however, are less likely to be affected. In sloping areas, earthquakes can trigger massive landslides. In areas with sand that is nearly saturated with water, seismic vibrations can cause the ground to behave like a liquid in a phenomenon called soil liquefaction. Soil liquefaction can cause trees and houses to fall over or to sink into the ground and underground pipes and tanks to rise to the surface. The type of ground material can affect the severity of an earthquake in an area. Ground motion is amplified in some soft soils, such as unconsolidated sediments. It is muted in more resistant materials, such as granite. Now, this guy is over an area where there is soil liquefaction, and as he goes around, he's moving the pocket of water, and you can see that it's starting to move. The more he steps, the more it pulls the water to the top. And you can see how much it moves. Here you see a building that, due to soil liquefaction, started to fall into the ground. And on the right, a more dramatic where a car was engulfed by soil liquefaction. A tsunami. Another type of hazard is called a tsunami, a large ocean wave generated by vertical motions of the. Now this is a still picture of, you can see the motion of the fault, and you can see it pushing water up into the air, and as it pushes the column of water up, it then creates a wave that then can hit the shore. If you look at it here in motion, you have the upward push. The motion of the fault causes a rift in the water, which then takes the water towards the shore. One thing that you will always see in a tsunami is you always have a shore erosion where it actually looks like it's sucking the water out, and that is because the water from up out is pulling so much water, it pulls it underneath, and then you get the larger wave. There's currently no completely reliable way to forecast the exact time and location of the next earthquake. Instead, earthquake forecasting is based on calculating the probability of an earthquake. The probability of an earthquake's occurrence is based on two factors: the history of earthquakes in an area and the rate at which strain builds up in the rocks. The probability of earthquakes in seismic belts is much more greater than elsewhere on Earth. The history of an area's seismic activity can be used to generate seismic risk maps like you see here. The darker the area, the more red, the more likely you are to have those types of earthquakes. And you can see them in Alaska, along the shore of California, all the way up through Washington. And then we have some in the middle of the country towards the Appalachian area. Earthquake recurrence rates along a fault can indicate whether the fault ruptures at a regular interval to generate similar earthquakes. Earthquakes in 1912 and 1999 happened on either side of Istanbul, Turkey. The earthquakes around the city area leave a seismic gap that indicates that an earthquake is likely to occur in that area. Seismic gaps are sections located along faults that are known to be active, but which have not experienced significant earthquakes for a very long time. The stress accumulated in a particular part of a fault, together with the amount of stress released during the last earthquake in a particular part of the fault, can be used to develop a stress accumulation map.